All right, so section 6.4, it's the last one for chapter 6. And basically what it does is we've been working with one dependent variable and now it's two dependent variables or more. So this includes like polar coordinates, cylindrical coordinates, and any coordinates that depend on time. This is the one that you're going to use the most. And reading through chapter 7, the textbook derived it like 3 times. So I'm going to consider this derivation kind of important to understand, and this one you should probably watch. It'll mirror 6.2, so if you watch 6.2, it'll make a lot of sense. But again, mainly the beginning and the ending equations are what's important if you want to just like go with that. Once you know what they are, you just go with it. You don't want to derive it every time. But the textbook is like, no, I would like to derive it every time. And I'm just like, yeah, you do you. So time to derive it one more time, I guess. Definitely not one more time. You'll be seeing a lot of this. So I kind of got it set up for us right here. So that basically just tells you what I told you. What we're going to be looking at it as is x is a function of u and y is a function of u. That u could be like time, theta, whatever. Um, so then what is going on from there is that we want a ds, much like in 6.2 and 6.1 for that matter. We also use that. So we're just writing it down in kind of like simple terms from there on out, and then we're making it a length. So we're taking the integral of it. That way we're going from one point to the other point all the way through. We're committing to our cent here. This is finally the section where we fully do solve that the two between 2 points problem, and it's going to be 3D. So basically the goal of what we're doing with this equation is to find the two functions x and y that are both dependent on u, and find where they make L a minimum. So we're just gonna go with it for that. So we're starting with the same thing that we started with in section 2, which is just this basic integral that the textbook gives us that's so generic that it means practically nothing, except we're about to manipulate it like there's no tomorrow, and then it's gonna all of a sudden it's gonna mean something. And we're gonna be proud of it. We're gonna send it off to college and we're gonna be so happy for it. And then its college is gonna get shut down because of coronavirus, and then it's gonna be quarantined, and it'll have to move back home. Um, that was real. So basically, we're starting off with just this little function right here. It's a big function, and it just says that there's a line that is a function of two functions dependent on a variable. That's all that says to us. And we're gonna do kind of the same faking it until we make it that we did in 6.2. So we're gonna add fake functions to arbitrary. We're gonna add arbitrary functions to arbitrary functions and make an arbitrary function. So I'm gonna write that down so y'all see what we're doing. So we're gonna do one for each, one for x and one for y. So x gets this cute little arbitrary function here, and the x of u will be the minimum shortest path arbitrary function. That's what we care about there. And we're going to use an alpha, and that's going to be the one thing that changes. So our two arbitrary functions are going to be fixed. They're going to be set. Whatever they are, they are. And hey, I'm back. Okay. We're going to call our second arbitrary. I don't like it. It's not doing it. It's not being nice to me. We're going to call our second arbitrary function of this epsilon. And epsilon is still going to be a function of u. And then for y, we're going to have y equals y of u plus beta, and beta is going to do the same thing as alpha, where it's going to vary so that our made up function doesn't have to. And here we're going to use that squiggly envoy. And squiggly envoy is going to be a function of u. So what we're doing with those is basically the same as what we did. Everything's going to be the same as what we did for 6.1. But the main condition in 6.2 in 6.2 was that for each of these, the derivative with respect to alpha is just 0, because alpha will give the minimum. Because when alpha is 0, you will get the minimum. And that's just sort of based on the core definition of the weird mental math we did, multiplying an arbitrary number by an arbitrary function and adding it to an arbitrary function to get an arbitrary function of arbitrary functions. It's really weird. It makes a lot more sense in 6.2. But like I said, the main things you're going to care about, I'll highlight them, is this function right here and then whatever's at the end. So we're going to set up two Euler-Lagrange equations for this. And the f is going to be inside, and it's going to be composed of, I'm highlighting green this time, of these two boys. All right. So I'm just going to kind of like write that out for y'all. So the two ones that we'll care about, oh, I don't want to use that color. I'm going to use blue. The two ones that we'll end up caring about are df dx, du, df, and dx prime. And this is because we have to deal with them separately with Euler-Lagrange. Euler-Lagrange is not like, and then we add them all together and they lived happily as family. No, it's not a family. This is separate. So what we're going to do then is we're going to take the derivative of the function of x with respect to y, and we're going to derive the function of x by y prime, and then derive it by function by u, which is the variable it cares about. And so we have to do them separately because it can, basically Euler-Lagrange can only handle one dimension at a time, but it does really good at doing each dimension quick and similar to the other ones, depending on your constraints and all that. So it's just easier to use in a lot of ways. So what we're gonna do now is we're actually gonna implement it. So we're gonna do the shortest path between 2 points again. But this time it's gonna get cool. I'm gonna put again because we've done this a lot. I've done this a lot today. Yeah, okay. So basically we're gonna start there with what we had up here. So, whoa, hey, stop that. So up here, I'm gonna take this boy right here, and we're gonna bring him down. And that's gonna be our f of x in this equation. So f of x, x prime, y, y prime, u. Yeah, that big boy is just gonna be x prime squared plus y prime squared. It's a lot less gross that way. Isn't that cute? So then what we're going to do is we're going to take those Euler-Lagranges, and I'm going to do the x first. So x is going to be d, d, u, df, dx prime. So this is going to be 0. And I'm going to do it in 2 steps like I've been doing. This is just going to be x prime. Nope, no, it's not. I have to. It's underneath the radical. I'm just being silly. Okay. The x prime over the square root x prime squared plus y prime squared. And I really wish it was the other. And so this we can obviously see is definitely going to be that. There is no u, which just means that this right here is equal to a constant. So we're going to set that equal to C1. That's the first equation we dealt with. And then we're going to go back to our y's. So here's that one. Oh, I did it wrong. Yeah. Ever realize you forgot something like a long time ago and you have to go back for it? So we're going to do the same thing. You end up with 0 again, still no y. And then du prime, y prime over basically the same thing. So x prime plus y prime. Now I can write it small. Great. And then you're going to see the same pattern pop up of this. So we're going to set that equal to C2. So now what the book has us do is, in order to combine, we're going to divide stars. Our second equation, but that is bad boys, by our first equation. And that's how we're going to combine the two. So when we do that, it's going to be pretty, huh? We end up getting C2 over C1, and it'll be equal to y prime over the square root of x prime squared plus y prime squared over x prime over the square root of x. We're going to move of x prime squared plus y prime squared. And then we're going to not have that ugly thing because those cancel. And we're just going to get C2 over C1 equals y prime over x prime. And what's cool about that is that y prime over x prime you can have rewritten as dy over dx. And what the book wants you to point out there is that this is a constant, and that constant is equal to m, because if you see here, we have our rise over our run. So we literally just found the slope of a line, and we cared enough to do it with respect to time, 2 dimensions. So that's what that does, and it points out that this m that we found is very important, and it's the sole ultimate goal of Lagrange or Euler-Lagrange equations is to find how each coordinate varies with time, or how the whole system together varies with time, which becomes a lot more relevant and cool later on. But I'm going to go ahead and write you all a general form. So we saw how all that worked, and the general form is what you're going to see in the book a lot. So it's going to be related, if I scroll back up here, to these guys, in the same way that it's related to that yellow highlighted section. Ooh, squeaky. Okay. So what I'm going to write out for you is I'm going to write out kind of like each thing to know. So we're going to define the Lagrange as a Lagrange equation that accounts for any Q1 dimension times all that. And then we're gonna say it can handle as many of those as it so pleases. And they're all gonna be in respect to time, just because that's nice. And that just means that there's enough Lagrange equations to go around. And then we're gonna write its S integral. So that will be equal to time 1 times time 2 of this Lagrange that we just did up here. So I'm going to give you a little arrow so I don't have to write that all again. And then integrated with respect to dt. Then the last one, so this is one of our important points. I'm not writing that again. Okay. This is this. And then what's cool is you end up getting a whole set of Euler-Lagrange equations. So the set, I'll write out the first few and then I'll just sort of do the dot kind of vibe, because it has, the way I have it set up is it has infinite amounts. dt. So the Lagrange is a script L, it's not a special letter. Just so you all know, there's no Greek thing going on here. It's just fancy. And then its next equation. So none of these equations are added together. They're all just like dealing with everything on their own terms. It's Q2. So I'm going to write there. That way you all can see the pattern. I like that I switched how I'm writing derivatives in the middle of writing them. Okay, and then that'll keep going on and on and on. And I'm gonna write the general one really nice, hopefully. So that the Lagrange of d n, where n, any number you so please, will be equal to d dt of the derivative of Lagrange with respect to that dimension's time derivative. So that's the zinger of this entire chapter right here. And it's going to keep bringing it back up in chapter 7. And it's going to keep deriving it for some reason. It just really wants you to remember that. So that's the goal, and that will show you how the coordinate system changes with time no matter how many coordinates you have. And the way it works is that will satisfy the action integral, which is what the book calls the whole S integral. It's like, where's it going to go? That the where's it going to go integral, it satisfies that as being stationary, and just since that, so basically the Lagrange equations satisfy that, which makes that happy, and the reason that that is happy is because it satisfies the Lagrange equation. So they just work in this little loop that can never be broken. So it's really hard to mess them up, and that's why they're useful. So that is all of chapter 6, guys.